Welcome back to the classroom. My name is Mr. Wong. Today we're going to be looking at Module 3, Waves and Thermodynamics, Inquiry Question 3, Sound Waves, and we're going to be analysing the qualitative and quantitative relationships of the wave nature of sound to explain beat frequency and the Doppler effect. As you recall, we talked about the different characteristics of mechanical waves and also electromagnetic waves. We talked about some particular behaviors such as refraction, reflection, diffraction, and superposition. Another thing that both of these share is the Doppler effect, which we'll explain in a second. And also with sound, we can see a concept, or can hear a concept called beat frequency. Just before we start, let me just go back on what we talked about with wave superposition. So with wave superposition, it's the idea that we have two waves of the same amplitude and they construct or interfere constructively. So they are moving in the opposite direction, or assume that they are combining at the same height, so the same maximum heights combining together. Or they can go through destructive interference where the wave effectively cancels each other out. So you have constructive, they'll increase the amplitude of the two waves because they are coming in phase, as we like to say. Or it can be destructive interference where the two waves have the same amplitude but they're in the opposite directions, hence they cancel each other out. So what does that have to do with sound waves? Well, actually beat frequency, when you hear certain tones, certain beats of different musical tones in musical instruments, there's a lot of constructive and destructive interference that is occurring. Now imagine you're trying to play a particular tone for your guitar or piano, and you try and play a particular frequency, but that particular frequency gives you sort of an in-between tone. Now the reason being is because the wave isn't quite in sync with each other, so it's not a complete constructive interference. You don't have that superposition. Instead, you have a little bit of frequency that's going in between the ideal frequency you want. That's what we mean by beat frequency. It's a particular tone that's in between the one that you want, and you'll find that there's a lot of constructive and deconstructive interference going on here. So this is kind of what you see here, and we're going to see and hear what that kind of sounds like as well. Okay, so today we're looking at beats and Doppler effect. You can always look up your textbook page for reference. Okay, now let's get started. So, feeling beat, what is beat frequency? So we know beat frequency as when two sources of sound, and this could be more than two sources, but usually two sources, with the same amplitude but have different frequencies, are heard together, and it causes a rhythmic change to the volume of the sound you're listening to. Okay, so you have the frequency of 100, you have the frequency of 120 Hertz. You can see they don't quite align very nicely with each other, and so when they interfere, they get this particular wave, which we call beats. So when in phase, obviously your amplitudes will double or increase. When it's out of phase, you get destructive interference, and so you get this sort of cancellation tone here. The variations in loudness that we see here, that's what we know as beats. So I'm going to try and show you what that looks like and what that sounds like using this software called Audacity. So let's have a go. Okay, this is my Audacity software, so I'm going to try and generate a tone. So I go to generate, press on tone. Doesn't really matter which one I use, but I'm going to go with frequency 440. Okay, and I am going to just zoom in just so you can see the type of tone, the type of wave I generate. So you can see a nice little sine wave going along like so. Now, if I try and play this, obviously you know how the tone goes, it'll go up and then go down in terms of the intensity of the sound, or the loudness, the volume. So let's give it a go.
So let's give it a go and listen to the tone we generate. So that's the tone of 440. We're going to add a second tone, same volume, so same amplitude, but slightly different frequency, and we'll see what happens here. So I'm going to go generate tone. I'm going to just change it very subtly. Okay, so let's just close it back in. You can see that we have a very subtle change in positioning between the waves. What that should show is that the volume will vary because the different amplitudes are going to cancel out at different points, and we'll see sort of a more stop-start type of a sound. So let's give it a listen. So in that one, it sounds a bit more like a bell, and that is what we mean by beat frequency. Okay, let's see if I can actually create this as a wave that's interfered to each other. Okay, so just make sure you select both waves. So select and select. Go to tracks. You have this option called mix. We're going to mix and render to a new track. Okay, now this is the actual wave we have. Okay, so you can you can't really see when we're really zoomed in, but when we zoom out, you can see that sort of beat tone right there. So let's just get rid of these two and start the beat for this one and see what we hear. Okay, so that's exactly the same as what we generated when we had the two waves constructed, and obviously it should be because this beat frequency is constructed from the two waves interfering with each other. So now let's go back and continue on with the mathematical calculations. Okay, so what we showed there was obviously the qualitative analysis, so this descriptive analysis of what beat frequency looks like. Where can we actually use it? Well, piano tuners will use this to make sure that they have the correct tune of the particular frequency that they're generating. Police radars use beat frequencies to work out the reflection of their radar or radio waves when they're tracking the movement of moving cars to see if it matches up. So the formula in which we use to analyze beat frequency, which is, again, like we said, the variation in loudness of sound when the waves superimpose with each other, it goes as F beat equals 2 absolute values F1 minus F2. Okay, now the thing that this would imply is if you have multiple, so if you have a beat frequency, okay, so if you have a beat frequency here, that means you can have two possible values. Okay, the fact that we're using absolute values here means in this response we can have two possible frequency combinations that generate this particular beat frequency we have here. Now it is measured in hertz, so don't forget. And now we are getting into the quantitative analysis, so using numbers to analyze the beat frequency. Okay, so let's go with question 1. So a musical instrument is played with a frequency of 359 hertz. Another instrument is played at the same time with a frequency of 361. What's the beat frequency that's heard? So obviously just substitute into our formula. F beat equals 2 the absolute value of that minus that. And also, because it is absolute values, we don't really need to worry too much about the placement of where each number is. Okay. So we have a beat frequency of 2 Hertz. So that's the fluctuation we're going to hear. 2 flutes are tuned up before performance. They notice a beat frequency of 2 Hertz. Perry knows that her flute plays a constant C at exactly 262 Hertz. What frequencies could the flute be playing? Okay, remember with beat frequency, the combinations we can get are two different values, okay? So we want to work out what frequency her flute is playing if she knows she needs to play it at 260. So our beat frequency is 2 Hertz. She has to be playing it at 262, and then X is whatever value she thinks her flute is playing at. Okay, now this is where we can work out this two exact values, or two values that the flute could be playing at. Okay, it could be playing at 2 Hertz higher than 262, or it can be playing at 2 Hertz smaller than 262. So let's try and show that working out. Okay, so what we have here is the fact that X here could either be 260 Hertz, as we can show 262 minus 260 will give us 2 Hertz, or it can be 264 Hertz, because if 264 Hertz minus 262 Hertz will also give you 2 Hertz. So that's what we mean by these beats, or these frequencies to generate these beats can give you two answers, 260 or 264 Hertz. Okay, next one. We have a flute and a clarinet sounding together, producing beats of frequency 5 Hertz. If the frequency of the note produced by the flute is that, calculate the possible frequencies. So as we said that the flute is trying to generate 240 Hertz, we have a beat of 5 Hertz. What combinations can we get? That means we could have a combination of 435 Hertz or a combination of 445 Hertz there. You have two violinists playing middle C, but one is actually producing a note at a frequency of 259. Beats are heard. Calculate the frequency of the beats. So again, as you can see, the actual calculations for this isn't overly difficult. I would say it's more important for you to understand how beat frequencies are generated. And that's with what our qualitative analysis we did earlier. Okay, so there's that. All right, the next bit we're going to talk about is the Doppler effect. And obviously, I'm just going to cut it into two sections for this video. So if you want to continue on listening to the Doppler effect, please go into the next video. Again, if not, again, welcome back to the classroom. Next lesson or next content we're talking about is Doppler effect.